Okay.
It's weird. Hi. Can you guys hear me okay? There, that's probably better. My name is Nancy Wolk. I work with Kim Arcand, and what I wanted to do is explain how we do our storytelling in the Chandra images that we do for a release. And unfortunately, you kind of got a preview of this, but the idea is how do we go from, oh, yes, I'm very short, sorry. How do you go from a raw image? How do you move to the next one?
Does this work?
Oh, it might be because it's off of there.
There we go. There we go.
To something very wow. So what I want to do is give you a little bit of our workflow. I'm going to focus on this particular image and go through what we did with it. So what's my workflow here? I first read the paper that we're trying to do a release on, because that will give me what we want to focus on. We then will reprocess the data. In X-rays, we can merge and prepare the data. I then will examine the raw data. Whoops, that was a little too soon. I will convert the data from FITs to TIFF files. Then I will combine, color, resize. I will find supporting data, and then revise, and revise. Lots of revisions. So if you don't have a paper to read, where do you start? That's fine, you don't need a paper. If you want to just make a beautiful picture, that's a reasonable goal to work towards. If you're doing something scientifically, you kind of want to know what your goal is. What do you want to highlight? What are you showcasing? If you don't have a paper, you can go to archive. That is how it's pronounced, despite the weird spelling. This is just archive.org. Do a search on this source that you want to do. There will be lots of papers. Pick one, read through the different, what are they focusing on? Decide what you want to work with. You can also just do a straight search engine on, okay, this is my source. What other images are out there? And while you're not going to duplicate those, it does give you different ideas of how different people have presented these data. So first thing that I like to do is take my X-ray material and I download the data from my archive. I reprocess it with the proper time correlation files. And the X-ray community, specifically CHOW for the Chandra Observatory, allows us to merge multiple observations of the same object. It does all the calibrations for you, equalizes everything, and this increases the signal to noise. Now, a lot of times I want other data to support this. So there's tons of archives out there. We have MAST, which has HST, JWST. Does it have Spitzer? I think there's some Spitzer in there. Robert can yell at me if I say this wrong. URSA, not sure if that's correct. That is over at Caltech with all the IR data. ESO has a ton of data out there, including all their major observatories. Sloan Digital Sky Survey, their data are available. Chandra uses something called Chaser, and Aladdin is also out there to use, which is related to the people who do SIMBAD. So this is not a complete list by any way, shape, or form. I didn't list any of the radio archives. These are the ones I use more often, but there are tons of data out there. If you need supporting data, go hunt for it. First thing I tend to do after reprocessing everything, I examine the data and I have to convert it from FITs because none of our imaging software works outside of FITs. I generally use DS9. I hope you guys can see that. In this image, this is what I got from the observer. Lots of black, itty bitty image. That's not very helpful. But I'm able to use this to determine where I want to extract the data, what I'm focused on, and I can also use this for aligning data later because I can use the world coordinate system and allows me to set the cursor in one window and it will move in the other images to the same location in WCS. There's also a simpler version, JS9, which allows you to also put in some JavaScript. And that is, I've got the URLs in here. You might want to write them down, but you might want to look at the slides later. Another thing that we use is FITS Liberator from NORLab. This one I use a lot I pinpoint my data down with DS9, and then I go into FITS Liberator to get my TIFF image. And if you want to use all free software, there's also Gimmick. And this is how I've been told it's pronounced, Gimmick. They have a lot of good tools in there that you can use. I'm going to do this very quick. For X-rays, we don't have a lot of photons. We're kind of the low photon people. So a lot of my things I will smooth. I will use Chow's wave detect algorithm that does AC smooth. Gimmick also has a smoothing, lots of smoothing, but I really like the anisotropic smoothing, which works really good for diffuse sources like nebulae. And to give you a quick idea of what I mean by smoothing, we recently put out an image of Uranus with the X-rays. That beautiful pink spot was originally 7 photons. And we did try to find an image to align it as best to where we were seeing the photons from. So color combine resize. I apologize, Robert, we did use the rainbow. What we tried to do is people say, oh, you're using pseudo color. And I say, no, we're shifting the X-rays to where our eyes could see it if we could see an X-rays. So generally the lower frequencies are going to be red, then we use green in the middle, blue for the higher ones. So in this particular case, our 0.4 keV to 0.7 keV, I did green. In blue are the 0.7 keV to 0.8 keV. And basically everything else is purple. Now we can add this all up and get this nice pretty image. And at this point you're like, wait, you said you put red to the lowest colors, the lowest frequencies. And that is true, but in this case, the paper is focusing on where the X-rays align with the Hubble data, particularly H-alpha. So for this image, we used red for the lowest energy, which was the H-alpha data. Now, this particular image was found in the ESA Hubble archive. 2 minutes, I'm going to speed this up then. So in this image, I was able to take this, align it with the other images from X-ray using DS9 and the information on the ESA Hubble page. Normally, we put our images with north up. Most of the Hubble and JWST images are the prettiest way possible, which means on their pages, they actually show you the orientation. Very important. So now the job is fine tune and revise with the editor that you like to use. I use Photoshop. So we revise, 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 and we come up with something that we think works best for showing the science. And you put it all together, you get this incredibly beautiful image. And what we're highlighting here are these shocks in the corners. I hope you can see where my mouse is. Those shocks align up with the H-alpha data. And what the authors are trying to show is how that shock is moving. The green data align with oxygen in X-rays. The blue data align with iron. And it turns out the purple does not have any sort of relation to the H-alpha at all. And so that is what they were trying to show. And on our release, that is what we're trying to pinpoint. So I just want to point out that much of this workflow is based on what you want to do with the image. In this case, I needed to highlight those two corners. And I had to work with the color palette that I thought would work best with the H-alpha data. Except for Photoshop, all the images, all the software are freely available on the web. Instead of Photoshop, you can use GIMP, Gimmick, or for Macintoshes, there's something called Micken, which is basically a little GIMP guy with Scottish stuff on him and plaids. But that actually incorporates some of the Gimmick tools into MicGimp. And since I'm out of time, I'm just going to leave you with thank you, and please visit our website. If you go to the photo album on our main page, that's where you'll find all our pretty images. Thank you.
I don't think we have time for questions.
Nope. Email me later or bug me after the session if you have questions.
And again, put questions into the Slack for the workshop, and we'll make sure people look at those.
Yeah.
Yes, is the camera adjusted? Yeah, that's good. All right. So I'm going to give a talk on scientific storytelling, okay? And we are astronomers, we are scientists, but we do tell stories, okay? If you're going to get your point across, no matter what you're doing, you must think in terms of storytelling, okay? So what is the first thing you talk about in storytelling? Is it the plot? Is it the big finish? Is it the climax? No, it's none of those. It is the audience, okay? You cannot tell a story unless you know what your audience is. So in your career, you will have your research audience, your research group, okay? Folks who know all the jargon, you can use shorthands with them. You can talk geek with them, okay? You can go out to a colloquium, okay? And recognize that there's gonna be a planetary scientist and a cosmologist sitting in the same audience, and you must speak to all of them. You can't talk the details of AGNs with a planetary scientist because they're not gonna be familiar with it, all right? You come to a conference, you get the same sort of thing. This is a eye poster that I gave in Hawaii. So I'm wearing a Hawaiian shirt, knowing my audience, right? Wearing the Hawaiian shirt for that. But also you might be giving a large plenary talk or something like that. How would you approach that differently going out on a plenary? If you are involved in a press conference, you will have a different audience. You're trying to convince writers to write about what you're talking about. If you go out to schools, then it's extremely different because the educational system has very specific strictures at each grade level. You got to know your grade level and the people that's going. If you're going to do museums, okay, then you're starting to get out to the public. But this is more the science interested public, the public that actually will take some of their leisure time and go out and learn a little bit of science. If you're lucky enough, maybe you'll do some television and movies. We got to do an IMAX film. This is the director of that IMAX film, Tony Myers. And we got to try and figure out how do you reach the general public? Again, more of a documentary public. We got to go out to the public and do a Guinness World Record at the South by Southwest a few years ago, 500 people of the general public. Got to think about what they're going to be able to handle. But most of the time when you go out to the public, it's going to be via things like YouTube or social media, okay? And then what is that audience looking for, okay? So, summary. Who is your audience? Why are they in attendance? What are they trying to get out of this? What science interest, attention, knowledge do they possess? And how do you get and keep their attention, okay? You must start with these ideas and then you can begin your presentation, all right? Now, this brings up the essential storytelling tension. Is the story you want to tell. I want to talk about these AGNs and the interaction between the disk around it and the thing, and then the magnetic flares that happen, all that, right? That's what you want to tell. You want to get to the details of your science, right? But what is the story the audience wants to hear? It might be cats playing the piano, okay? Who knows? And then there's what I really focus on is the story the audience is capable of understanding. How far can I push them without going into, yeah, boring old science guy, right? So you got to try and work on that and that. All right. So to do that, identify your messages, okay? And I always come up with 3 types of messages. One is the primary message, one that I hope everyone will get. I sometimes call this the big and dumb, okay? Then there's your secondary message that you sort of, hope many will get it. If they're interested and they're paying attention, they'll get that second message. And then the tertiary message is those who are really interested in it will come up with this. And overall, okay, people hate me for this, but I am a massive insistence that visual messages are the strongest, okay? You look at that, you are inside the Orion Nebula. That's cool, right? That gets you. That's a bunch of text, okay? It's nice. So my reason why people hate me for this is I never write my script until the end, okay? I design all the visuals and then I add script on top of those visuals. And some people think that's just the craziest way to work. Hey, it's worked for me for 25 years. So I think it's a thing I'll stick with. All right. So now you're going to construct a story, all right? And like, this is just normal good storytelling, okay? Explain the setting and the background, okay? Then from there, build your sequence of ideas, okay? And for us as scientists, it's really important to pull those ideas on top of one another. You have to scaffold them, okay? Start with the simple ideas, build to the bigger ideas, okay? Come to a conclusion, all right? Too many science talks I see end up putting out all these facts and it's like, well, what's my takeaway here? You got to come to the conclusion and then always review and summarize what you're doing there, okay? So if you go into TV reporting, this is the creed that they come up with. We had somebody from TV reporting work with us at Space Telescope a few years ago. Tell them what they're going to tell them. Tell them the story, and then tell them what you told them. That's real, and it just, I can't stand it, but that's actually when you watch TV news, that's what they do, okay? They're coming up after the break, and they preview the story, right? And then they do the story, and then after they repeat all the things. And it's a standard thing for getting across to the American public. I don't actually advocate it, but some sort of this is making sure that you actually come to your conclusions. So here is a visualization we did, and I'm just going to scan through it. All right, and so we start with the Whirlpool galaxy, and then we take it sideways, and then we spin it around, and we show you what's like invisible and infrared and X-ray, and we go through the various wavelengths for it, okay? So what is the primary message we're trying to get across here? Well, it was done in that first camera move, that it's a pancake, that the Whirlpool galaxy is shaped like a pancake. The secondary and tertiary messages are about the different wavelengths and what you see in the various wavelengths about it, but really have basic, simple expectations of what the public can understand. The visual message that it's shaped like a pancake is really the primary that I'm going for here. All right, and you're doing your background, okay? Make sure you start with the forest and not the trees, okay? If you're going to talk about things, you've got to introduce the category of the objects rather than going to that one object that you really want to focus on. And I will tell the people who do my public lecture series that often half of the talk can be just that background, pulling people in to set the full setting, okay? And, generally, you can try to get the extra jargon in there, but you really want to avoid it in your background type stuff, okay? So here is the opening of an IMAX short film we did.
Galaxies are like islands in the sea of space. They glow with the light of billions of suns. The Hubble telescope reveals nearby galaxies in exquisite detail. Galaxies like these fill the universe.
Okay, so before the title is fully done, we've gone through and talked about what a galaxy is, because most of your audience doesn't know what a galaxy is. I'm sorry that most of the public doesn't know what a galaxy is. They mix solar systems with galaxies. I blame Super Mario. Super Mario Galaxy is the worst thing for astronomy education that ever happened, okay? Because those are solar systems, they're not galaxies, okay? But every time you do something about galaxies and you really want to do it right, you actually have to explain what a galaxy is, okay? It's a pain in the ass, but that's life, okay? Another thing that works really well is zooms, okay? So I'm just going to show you this. So we often start with the constellations, and then for this one, we show Eta Car brightening, and then we just zoom in, and the audience just loves these zooms, okay? It gives you spatial context, okay, about what's going on, and we zoom on down until we get to Eta Car in the Carina Nebula, okay? Spatial context, don't forget this. We're always used to thinking about individual objects in the sky. The public thinks constellations, okay? To get down to that object, you got a nice 30-second zoom, and the public just eats it up. It's a lot of fun, okay? All right, so now we're going to talk about that scaffolding, okay? Going from the simple ideas to the complex. I will often work backwards, where I start with, all right, I want them to understand this idea. What do I have to set up for them in advance, okay? You've got to figure out your prerequisite ideas. This is something I learned working with educators for decades, and they kept pounding into me, no, at sixth grade, they're not going to understand this until you explain this and this before, okay? It works. It's frustrating to have to go through all that, but it really gets you through the prereqs. And as I say here, the payoff is really huge when they get it. All right, so in our film about the ultra deep field, one of the most important things is to understand that these galaxies in the ultra deep field are at many different distances. So we worked really hard. All right, come on. There we go. All right, we worked really hard to develop a sequence where we take that image and then we stretch it out into 3D, okay? That visual sequence, bam, hits it in the viewer's head that these aren't galaxies in one image, they're actually stretched out across the universe. And when we got that visual, we said, oh, now we got them. Now they're going to start to understand. And when we fly through it, they'll actually understand that we're flying out into space. And then we can start to bring in, hey, but we're also flying back into time, and so on and so forth in the scaffolding of that. All right, then always summarize, okay? And it's something we sort of forget to do because we've gotten to a point and we've reached our scientific result that we want to get to, but then you got to stop, go back and recapitulate the whole thing. You don't have to do the whole TV reporter thing, but stating your final message clearly is important, especially for the public, okay? Because the last thing is what they're going to remember. So I'll show you an example from our Crab Nebula. And here we talk about the visible, the infrared, and the X-ray, and then we spin it in 3D. So you see that the Crab Nebula is spinning in 3D. And finally, I hit them with the punch sentence at the very end, which is this Crab Nebula composite image illustrates the interconnected emissions from the Pulsar Wind Nebula. That was the sentence I chose as like, that's the last thing I want them to understand, that it's multi-wavelength and they're interconnected and there's this Russian doll structure like that. Works really well. Okay. Okay, so now some useful techniques. What's my time? 2 minutes. Fantastic. We're right on time. All right. Useful techniques. 1, lie as little as possible. Okay. You are going to lie in your visualizations. You can't help it. You're going to have flying it faster than the speed of light. There's a huge range of length scales in the universe. There is a huge range of time scales. You want to see the formation of the solar system? Fine, watch the Earth spin 500 million times, right? No, you're not going to do that, okay? For example, in the Flight to Star Cluster Westerlund 2, we fly into the star cluster, right? That star cluster is 7,000 light years away. If I put the stars at their actual distances, it'd be boring as hell to get before we got there, and then we'd be crumbing through it, okay? So our speed across the universe is, but when we do this, we try not to distort the main messages with that, okay? So simplify, keep it as simple as possible. there is cognitive overload. You can put too many ideas into people's heads and they start to turn off, okay? Also, my stuff has visuals, it sometimes has narration, it has music, okay? You want to give them that full emotional experience, right? But you can still overload them. You've got to give everything is slow in what I produce because you're reading screen, you're watching the visuals, you're hearing music, and you can't overload them too much. For example, you just went flying through all these galaxies. You saw things. I was like, all right, now, boom, just pop up 6 galaxies that show the main message, that show the development of from the red dot galaxies to the galaxies in the nearby universe. Just try and present it as simply as possible for your summary. Making it relevant, we at Hubble are known for using pop culture references. Nothing is beneath us. I'm sorry. July 4th, we do exploding stars. We did a snow globe one year. We even did this for Star Wars Day. Let's get over here. And we went in a double-bladed lightsaber, the Stellar Jetson HH-24. Okay, don't be too proud. They love this on the internet. Okay, all right. Finally, plus it up. This is something I learned from Pixar, and if you want a really good management book, Ed Catmull's book on running Pixar is fantastic. The plus it up idea is once you've got it working, see if you can make it just that little bit better, but only after you've got it working, okay? If you try this too early, you're gonna mess it up, okay? Don't undercut and distract from the main messages. All right, so I'm gonna skip that. There we go. Always use test audiences. And don't use just your friends. Use people who you don't know. I grab random people around the building, pull them into my office. I bring in educators, I bring in designers. I'd bring in the janitors if they'd come in, okay? Just so you get lots and lots of different reactions, and never tell them your thoughts before they give you theirs, okay? Otherwise their feedback's gonna be somewhat parroting what you say, okay? And so finally, last slide, and for effective visualizations, understand your audience. Tell your story with defined messages, provide adequate background, scaffold the ideas to bring them to that wonderful conclusion, but clearly state that conclusion. All right, and I will post my slides on the Slack channel eventually, but thank you very much.
Thanks, Rick. So I think we should hold the discussion.
Yes, please put questions into the Slack channel, because as I expected, I went fully into my time.
Probably at the end of this session.
And Gordon says to remind you that you can come up to me and talk to me at the end of this session. All right. So Rutu, where are you? No, Robert?
Visualization.
I thought that they got switched.
That's what I'm looking at the Google sheet. So
All right, Robert, you switched things on me. All right, where is?
then Rutu after that.
We don't have time in the session for that, do we?
We're running about 5 minutes behind.
Okay, no, but I mean, where's the Zoom?
Okay, let me share my.
All right, I got to stop sharing. That's what I have to do. There we go. Okay, Robert, take it away.
Yes, you've shared enough for now. Hi there. So I'm going to sort of pick up where Frank left off
All right,
here,
Robert,
and
stop your share for a second.
Okay.
I have to pin your video.
Oh, okay. Finally, arrange my windows while you're doing that.
You have to stop sharing
I have to stop sharing.
before I can pin your video.
Okay, there. All right.
Okay,
Ready?
now go.
Okay. So yeah, I'm going to pick up where Frank was going, but with while Frank is data focused, I'm going to be focused on illustration and balancing aesthetics and meaning in astronomy illustrations. So just quickly, my career trajectory, starting from my early inspirations, kind of equal parts Star Trek and Cosmos, career in research astronomy, but also career in art and illustration, going from analog airbrush and photography to Photoshop and 3D graphics, into the career that Frank has so cleverly dubbed being an astrophysicist. And I've been doing this for about 20 years, working first primarily on the kinds of things that Nancy was talking about, taking data, rendering it as imagery, but more and more I find myself called to do illustrations, because sometimes the data can just beautifully tell the story on its own, but sometimes it really needs help because it only is meaningful to people maybe in that specific subfield of astronomy. Recently, I had the chance to stumble across some of my early work, circa 1979, when I believe this is my first ever painted galaxy in airbrush. And when I rediscovered this piece, I was actually kind of horrified at how really not realistic it was. In particular, the core of the galaxy was just this big mushy glow that had no well-defined center. And I'm just thinking, what was I thinking? But then I realized it was a product of its time, because in the 70s, the images I saw of galaxies were photographic, and they were almost always overexposed in the center in order to bring out the outer regions. And I was literally unaware that galaxies had sharply peaked centers, because that imagery did not have the dynamic range to reveal that to me. And that, as a result, my illustration failed to represent something really physically important about the geography of galaxies, which was sort of this moment of looking back historically and realizing visualizations can deeply affect our mental geography of the universe. And that is especially true for how we present it in artwork. Again, understanding your audience is important when you are approaching this, because there's sort of a continuum, 3 categories we look at, I think, in our work: education, set in classrooms, informal education in museums, and communications in the news media. And these are importantly distinct audiences because, among other things, there's a certain amount of captivity involved in the audience, where in education, you have kids who can't get away from you. They're stuck, but they are also facilitated. And how you approach illustration in that environment is not necessarily going to be the same as for communications, where you are in a completely competitive, trying to get the next click instead of someone who might instead go to the next Guardians of the Galaxy trailer. Visualizations for communication serve 3 important purposes. They are to grab your attention initially, because you don't want to lose focus and have people never even notice the article was there. They then need to illustrate a basic concept, giving you at least a hint of what the story is about, leading people, hopefully, to read the article and learn more in depth. This is the kind of work that I have been doing for, in support of Spitzer press releases and other missions. It got me to think about this as a data art continuum, where somehow on one side you had pure data that was unaesthetic, and on the other side things that were purely aesthetic that had no informational content whatsoever. But I realized that was an oversimplification of at least what could be 2 axes of visual engagement on one and science content or informational content on the other. And you can sort of have fun placing, data plots in one place, Guardians of the Galaxy, which is engaging, but nothing of value scientifically whatsoever. Other things that have neither content nor value. And, place some of the other things where you want. But for me, where astronomy visualization and illustration becomes interesting in the AstroViz concept is trying to push as far as you can to the extremes of both of these axes. Can you maximize what you're saying in the illustration while maintaining that high degree of engagement in what you're doing? This led me to think about how we have successfully been doing this for our press releases for many years now. And it led me to think of the AstroViz trilogy, or the AstroViz trinity, a way of balancing these different concerns. Of course, you've got the science that defines the content that you're trying to get to in the first place. You have a communications aspect to this of understanding your audience, and you have an art aspect of this of understanding the aesthetics. And I think this isn't just an abstraction. I think you literally need people at the table actively advocating for each of these axes if you're going to pinch and pull what you create to arrive at a compromise that maybe no one's in this trinity is completely happy with, but in the art of true compromise will probably be the most effective communications product if it's done. Now, of course, science gives you the material that you're starting with to begin with. A communications expert will help to really understand and identify that audience that you're trying to address, whether it's education or informal ed or whatever, and to craft a narrative from that science, a subset of what you think you can communicate to that audience. And of course, the role of the artist is to identify the visual concepts and to increase the visual appeal. But at all stages, this has to be a constant interaction back and forth and always touchstoning to the science. So another way that I have thought about this for years is how I approach illustration is that you sort of can throw down, imagine throwing down like check marks of all the things you actually know are in the paper or are known to be true of the science. To that, of course, there are lots of things you know aren't true, are completely excluded by the data or the science at that point. There's many, many more things that are possibilities that are consistent with but not supported by, right? These are the possibilities. Now, as an artist, you can't draw everything. You have to, an exoplanet can have water or it can't. It can't have both, right? It can't be in both states. So you have to make some choices and you have to sort of draw a circle around some of this and say, these are the things we're going to encompass in the artwork. Now notice I've actually included a couple of red X's in here, and that's because sometimes you may actually show things that are inaccurate if they are inaccurate in the service of greater communication. For instance, if you are doing a black hole and you do it exactly to scale, you might not even see the black hole in the illustration. So you may choose to exaggerate scale in order to successfully communicate an idea that would be lost otherwise. Now, art, of course, is the thing that fills in all the gaps to make it a complete picture, and especially on the gaps between all the things that might possibly be. And in some way, if you do this right, your possibilities could be thought of as hypotheses in the art, because my colleague Bob Benjamin once promoted in a talk of his that the art is like a hypothesis of what could be the case. It's testable. It shows a commitment to a particular idea, and then something that might be borne out in data. Well, with that transition, I'll talk about possibly one of my most famous illustrations, one of an illustration of the Milky Way. Now, one might ask, why do we need to illustrate the Milky Way? Because we're in it. We have the most complete mappings from the inside of anything in astronomy. But the challenge of understanding the Milky Way is akin to being in the middle of Times Square and being asked from that one vantage point, draw a map of Manhattan. Obviously, you can be very accurate locally, but it gets less and less certain as you go down these long sight lines, and you have to extrapolate behind buildings. That's kind of the same process we have to go through in understanding what the Milky Way will look like behind the dust clouds and disentangling rotational vectors from radio data. So in 2005, Bob and I worked on a release where we were focused on just a couple of key things. The sun being at a particular location in our spiral galaxy, and that there was a bar that was now understood more clearly in the very center. That was really all of the bullets we put into this. I added in some spiral arms that were roughly there to communicate this, but this is all. However, it appeared everywhere. Everyone ran with this as like, this is the map of the Milky Way. Then I started getting emails from scientists who were like, oh, you didn't see my H1 study. Oh, you didn't see my CO study. Oh, you didn't see my dynamical study. And so all of a sudden, Bob and I were like, oh, we have to do penance for this because we didn't really mean to map out the Milky Way. We didn't try. Bob organized a workshop at 2008 and actually brought in researchers from all disciplines to try to correlate all of these different disparate studies of Milky Way structure. And from that, we produced this illustration of the Milky Way as we best could argue it was structured at that point in time. Now, this is a complete picture, even though, of course, there are huge regions we knew nothing about. The radial velocity tells us nothing on the far side of the galaxy. But Bob actually agreed with me that this needed to be a complete piece of art, that if we were trying to be purely accurate with only the things we knew, it would be incomplete, it would confuse people, and we wanted people to really get that gestalt of our Milky Way as a complete galaxy. So, interestingly enough, there are features in that art that were subsequently discovered after 2008 in other data sets, including, in particular, Thomas Dane had mapped out a new arm in H1 that was so closely correlated to the art I had, he contacted me to make sure that I didn't have privileged access to a data set he wasn't aware of before he published the paper. Amusingly, it was pure aesthetics and logarithmic spirals and the aesthetics of symmetry that predicted that arm, but it was a hypothesis that was borne out. Now, another area that I find I'm doing a lot of illustration these days is black holes. There's so much interest in them and so many exciting results. Now, pop culture has shown us black holes for a long time, and I've realized that they kind of fall into three categories: bowling balls, bathtub drains, and if you're J.J. Abrams trying unsuccessfully to do Star Trek, flat swirly things with lots of bright lens flares. Well, honestly, classic AstroViz is pretty much the same. I've done my fair share of bowling balls. They're bathtub drains, which are not unmotivated in this abstraction of taking a space-time diagram and just thinking of that as a literal three-dimensional map of what a black hole should look like. It's understandable how people would arrive at that. But even so, we've known for over 100 years that black holes warp light. So why was that missing in visualization? Well, it's challenging for one. And it's also not what people expected to see. And this is a surprisingly difficult thing to overcome sometimes, because even with some early work that we did in Spitzer, I was always trying to push for things to at least give a hint of gravitational warping. And I got pushback from the communications team that, well, people don't understand that they just want to see it as a black ball. And I'm like, well, that's missing out part of the idea here. We actually put out a video starring Michelle Fowler in 2008 called Spaceship Spitzer, which to my knowledge is the first time a spaceship was ever shown orbiting a black hole that actually warped and refracted light. And the producer, Tim Pyle, actually pushed really hard against me because he didn't want to do this because it wasn't what he expected black holes to look like because of what he had seen up to that point. Of course, that all changed in 2014 with the movie Interstellar, where a director was actually interested in talking to a scientist to understand what they would look like. And by producing a movie version of the light refraction around, gravitational refraction around a black hole that was done so accurately that multiple peer-reviewed science papers came out of it, it forever changed now how even pop culture sees it. As I see it, if even Star Trek can get it right in at least 2 different shows, how can we do any less? Just for some of the mechanisms, I used to do this. Long ago, I decided that you could sort of build a refractive funnel-shaped lens to get some of the characteristics of a black hole. It's not perfect. You couldn't bend the light more than 90 degrees, but it got, it gave you an Einstein ring. It gave you a lot of the basics. And I used this successfully for a lot of my early stuff. It wasn't perfect. You would get artifacts, but at least it got in the ballpark of what we were trying to get to. More recently, I've been focused a lot more on, could we do a better job of this, where we could we have a sort of simple CG model that would bend light paths more completely around, like you would expect.
2 minutes, Robert.
What's that?
2 minutes.
2 minutes. And for this, I found there are nested spherical lenses can give you something very close to this. And this is a technique I learned in shifting to Blender as a 3D application recently and finding there's a tremendous resource of education materials online. So in using this, I've now been able to up the game in my black hole visualizations with some pretty simple optic trees, some procedural geometries that now really get us to a point where I can render on my desktop something that is at least qualitatively getting us to what we want to see in the refraction around a black hole. So I could have a whole other talk on the power of Blender, but basically now we can get in the same ballpark qualitatively as the sort of things you get from full-on relativistic ray tracing done on supercomputer clusters. And so when it comes to bathtub drains and bowling balls, I have to say for me, it's never again. I will just race quickly through exoplanets as another area we've done a lot of visualization, because again, exoplanets, the data don't tell the story that will get you on the cover of the New York Times. It's the artwork that sells the idea of worlds that we are starting to understand something about. TRAPPIST-1 is a system that Spitzer discovered many of the Earth-sized planets, and I had the opportunity to work on the nature cover, where in this case, the bullet points of the science we wanted to get in were incorporated into elements in this illustration to communicate things like habitable zone, color temperature of the star, relative scaling of the planets. And it worked effectively for getting our science messages across in a creative way. But science is always changing. And so it only took a year before the best guesses of what these planets might be changed. And so the art has to change with the science. But there are other ways of doing this art too. There can be much more fanciful ways that are evocative, like the work that the Exoplanet Travel Agency at JPL does and Joby Harris to really engage you in this. I will say the planet I've done the most renderings of is 55 Cancri E, which it seems like every year or two, there's a completely different focus on what the science result is. And I have done so many different versions of that. Joby has done one as well. That the beauty of this is it actually captures the historical science of how our understanding is changing. So it doesn't, I never mind throwing out my old art to do new art, because I think that's part of the visual record of how science does evolve over time as we do these illustrations. And that's one of their important roles. And with that, I will wrap it up.
Thank you, Robert. So we'll hold questions till the break, and then if anybody wants to chat with Robert, you can come up here and interact then. The next talk.
Rutu, Rutu, now you're up. Sorry, I got my stuff mixed up. Okay, well, good. I called you and you were here, and I was like, oh my God, did we make something? And yes, I made a mistake. First time I've made a mistake. Just ask my wife.
The first for everything.
Okay. Oh, I did it again. I started the PowerPoint before starting the screen share.
Second mistake.
No. So there we go.
So just
Zoom.
I have 10 minutes to actually talk.
Yes,
And
you have
then-
10 minutes to actually talk. Don't worry, we're not going to, we're not going to penalize you for me not being able to get this to go smoothly.
Oh, no, it's like it wasn't talk plus questions.
Well, it usually should be talk, includes questions. All right, so Rutu.
Right, thank you. Hi, everyone. I'm Rutu Das. I'm going to be talking to you about one of oh, wait, am I supposed to be talking to this?
Yeah.
Oh, okay. Hi, is this better? Thank you. Hi, I'm Rutu Das. I'm going to be talking to you about one of NASA's Universe of Learning's current products that's going on right now, called the Astrophoto Challenge. And I think you guys all heard a little bit about Universe of Learning before, right? I believe Gordon talked about it. So I'm not going to talk too much about it, but if you remember, we want to connect the public to NASA data and help them experience astrophysics. So the Astrophoto Challenge is something that lets you create your own astronomical image. And it runs anywhere from once to twice a year. We've sort of gone back and forth, but right now it's running twice a year. We finished last season's, and now we are inviting the public to make pictures of the Pillars of Creation and the Eagle Nebula. Now, this is built as a general public outreach thing, but we actually incorporate a lot of the same visualization skills that go into making the actual, the images of space that get published on any of the NASA websites, just on a slightly more simplified interface to work with. So we've got two parts to this challenge. One is the NASA data challenge. So we give users all manner of NASA data that we have, or not all, maybe not all, but many of the pieces of NASA data that we have on this object. Let them use the actual FITS files and play around with them. Well, FITS file images. I don't know if I don't think we actually let them download the numbers, but they can play around with the images. And so if you can see, I sort of had to cut off the screen here, but we have mid-infrared, near-infrared visible, we have X-ray, so there's Chandra in here, there's Spitzer in here, there is, of course, JWST in here, because we wanted to include that this time. So users can actually use all of these different layers and make their own multi-wavelength images. And we're going to talk a little bit more about that in a bit. And there's also this part called the Micro Observatory Challenge. Now, Micro Observatory is a set of, currently, I want to say 3 telescopes online around the world, maybe 4 if I'm wrong, but I think there are 3 around the world, ground-based. And you can go and request your own image of something. There's a list of possible things you can request, and one of them is the Eagle Nebula. And users can request the image. The next night, one of our telescopes will take an image and send it to whoever requested it. So it's like your very own image. It's not a NASA telescope taking it for everybody. You get that image and then you get to play around with it and process it. So, as I said, I can play it, yeah. Our targets this time, I'm gonna mute because I don't actually know if there's volume here, but yeah, so we start out with the Eagle Nebula. This is the far out view, and you can get this from the micro observatory telescopes. We then zoom in and you have like a closer up, but not quite just the pillars. You have the surrounding area as well, a wider field. And we have various data sets with this field. And then you can zoom in even closer and get just the pillars. And we have these 3 different fields of view. Actually, it also helps illustrate how, not every telescope has the same field of view. We have different sizes of the patch of sky that we can look at. So great for the public to see that because, most people think, oh, we point the telescope and we take a photo and it comes out beautifully like this, which if you're here, obviously, it doesn't. So we let them play with the different wavelengths and we let them play with the different fields of view. Why is this not going there? There we go. Okay, so yeah, as I said, we have the pillars of creation and the wider Eagle Nebula. And by the way, well, these are photos I took, I meant to say this before. This one over here is actually something I made out of the data sets that we have on there. From the challenge, which is live now. As you can tell, I'm not the best visualization artist. I understand the science, but you can sort of just make out the pillars. But that's the whole point. Like, not all scientists are good artists. Actually, many of them aren't, me included. And it's to encourage everybody to try to do this, to try to see, it's what kind of art can you make, but also what are the features what are the scientific features you can come up with by changing around things with how you do the visualization. So yeah, these are our targets. And I'm gonna play a little thing about, this is a demo of somebody doing this is actually Mary DeSalle, who is doing, she leads Micro Observatory. And she is basically taking some of the NASA data sets. She's already made a 3-color version of the Hubble data here. And we're gonna see how she blends it, I believe with X-ray. And, so yeah, she's got the Hubble. Can I look this up by any chance? No, okay. Yeah, she's got that. And then you can go and choose any of the other ones. Oh, Spitzer, I was wrong. Okay. So we get a mid-infrared, I believe. And you have this image blending panel. You can stop your blending. You can process the individual image that you just pulled up, change the contrast or whatever. You can change the color scheme. There are some fun ones to play with. And then you can blend it. She already had the Hubble set up. But as you can see, they're not lined up because, of course, our fields of view are different. But we make this handy little tool to let people align their images using all the metadata in the bits files. This is actually, if this looks familiar to you, this interface, if you've used DS9, it's similar, but this is called JS9 4L. It's a for learners sort of version. So we've simplified things, but you can do several similar things, but like easily align things like this and create something of beauty with it, without needing to really get into the nitty-gritty of DS9. And this is in Micro Observatory. If you go to the Micro Observatory page, you can request a target. We have stars and nebulae and star clusters and other galaxies. You can choose how long your exposure should be. This one is actually for the Carina Nebula, which was our target last time around, this past summer. Because when I made this, I also made this for a Hyperwall talk. So when I made this, we didn't have this video yet for the pillars of creation. So yeah, and then, you put in your info and you get your own image. So this is one I made of just going through how you can process an individual image. If you, for some reason, couldn't request your own image, you can use that. You can change the scaling, you can do linear, which nobody here in their right mind would do. I'm going to stick with the log scale that they gave us. You can change the low and high brightness. You can just see the Eagle Nebula starting to flicker into existence over there. And there's contrast, there's the bias. You can change around all of these things. And I was just trying to reach this. I had seen, you see that like one flicker of the Eagle Nebula. Okay, cool. And this is, by the way, the view you get from those ground-based micro-observatory telescopes. 1 minute. Okay, thanks. So yeah, I'm using the planner because I'm using a trackpad, but you can use like your mouse if you have one. You can change color, and I think I've made this too long. So what I do is just, move forward. So you can pick a color. You can also, interestingly, invert the color map, which doesn't look as spacey, but hey, you can see the structures over here. See, like now in this bright, I actually find the brighter color is easier to, you can make out the actual structure of the nebula. So this is a great way to show people like the scientific features that you can see when you're starting to do artwork. And I'm going to stop this here because I made this too long. But okay, so yeah, we actually, it's called the Astrophoto Challenge. We actually picked some standout entries.
Your very own expression.
Video. We picked some standout entries and showcase them so the public gets to be like, ooh, I made a cool image, and it's showcased. But what, we have additional resources all on the website. This could just, yeah, so how can you use this and get involved? Sorry, I will take like 30 seconds more. Well, you can, get the public to make their own image, but if you're an educator, you can like give your class a chance to get a taste of how to make their own image. You could play around with it to find your own features in Eagle Nebula or pillars. And you can use it for outreach, of course. And if you'd like to get involved, we do have scientists talking about the science behind what we're behind our targets. So this is an example from the previous challenge. If you're interested, we need people to provide feedback on these entries. And if you're interested, as Gordon said earlier, you can volunteer with NASA's Universe of Learning. And I'm going to just stop here because that's actually it. And I don't need to talk about more Universe of Learning.
Thank you, Rutu. Thanks for all the speakers in this session. So we're going to take a 5-minute break. We'll come back at 3:06 Pacific time, for those of you who may not remember what time zone you're in. Please come up if you want to talk to Robert here on Zoom, or reach out to Rutu or Frank or Nance during this break if you want to follow up. We'll resume at 3:06.